Hello everyone. Welcome today to the Blockchain Consensus Algorithms talk. First of all, a quick note, we will be recording this talk, so if you have any issues with the back of your head being recorded, please let us know. Otherwise, I'll now pass you over to Vishal, who will be talking you through all about consensus.
Okay, hi everyone. Can you hear me? Yeah. So I'll be talking to you guys about blockchain consensus algorithms. Hopefully, some of you have attended some of our previous talks about an introduction to blockchain and more or less how it works. But even if you've not, we'll be introducing it again lightly here. So the stuff I'll be talking about, I'll be giving an overview of verification in blockchain, comparing blockchain to databases. As quite a few people, when you bring up blockchain, they just ask, why not just use a database? In essence, they just say blockchain is a slow database. So we'll be talking about that. And then blockchain versus distributed databases. And then we'll be bringing in consensus algorithms. So we'll talk about proof of work, which is basically the first consensus algorithm, which came out in 2008 along with Bitcoin. On from that is proof of useful work, which we'll talk about, proof of elapsed time, and proof of stake. So let's go on with that. So, overview of verification. There are two key areas of verification that we want to talk about in the blockchain society. First would be verification of communications between one node and the rest of the network. Let's say you engage in a transaction, you want to make sure you can securely transfer information regarding the transaction you've committed to the rest of the network, and make sure that received it properly. Make sure there's confirmation and verification there. You also want to verify that the new block being added to the blockchain does not contain any fictitious transactions, and that it's that everybody has the same information, so there's no conflicts there. That's the second one, where consensus comes in, and that's what we'll be focusing on today. But first, just a quick overview of just verification of communications between individual nodes. This is just an example. There's a lot of implementations, but hopefully we'll be going into a bit more depth on this in a talk coming up with CyberSoc in February. But yeah, so we can see we're using AES, RSA, hash functions, and digital standard algorithms to ensure the data is transferred properly. Now, talking about blockchain versus databases, it's true databases are much faster, and storing information in a database is much cheaper. If you compare, let's say a 250 gigabyte SSD costs about $80. Storage on Ethereum, 250 gigabytes would cost about $84 million. It's a bit more expensive. Might put you in a bit of debt, but it's about 1 million times more expensive there. And yeah, SSDs are also much faster, and so are databases. So why would you consider blockchain? Well, that's because databases have their own problems. For example, there's centralization. If a malicious actor takes over a single node, they can take over the entire system. And if there's a single failed node, the entire system collapses. And obviously there's issues in regards to auditability and verification of data. You want to make sure everything's, you want to make sure there's change logs for everything and so on. And of course you can cover for most of this by just having data replication, but there's still a lot of problems that occur. So you might think, why not just use a distributed database in that case, which are also in general much faster than blockchain. And in general, distributed databases and blockchains try to solve a lot of the same problems. But they have a lot of problems themselves, such as consistency issues. you want to avoid conflict resolution. This conflict resolution issues that often occur with distributed databases with nodes being at larger locations. There's a lot of message queuing issues, so on. There's also the fact that distributed databases focus on, rely on most, if not all, nodes being trustworthy. You don't account for there being a potentially malicious node that's actively trying to compromise the system. And of course, they don't support smart contracts. Blockchain mostly tries to solve the second problem there, which is the issue of trust. They provide what we call trustlessness in the system. So blockchain asks for transaction consistency, auditability using workflow trees, and data integrity. So consensus algorithms are what allow for data integrity. They allow consistency without relying on all nodes being trustworthy. You can have, as long as you don't have to trust another node to be able to engage in transactions with them. And when this is just an example of a Merkle tree here. So that's just an example of Merkle tree on the left, which comes into auditability. So essentially what we have is we get the hashes from several different blocks, put them together to create a new hash, and so on until we get a hash that is basically a hash of all the other hashes. So we get Merkle root, which we can, as long as that, we can use that to make sure that we have the latest data, to make sure that nothing has been tampered with from a previous block. So trustlessness, what we mean by that is that no node needs to trust another node to participate in the network. So the first consensus algorithm we'll be talking about is the one used in Bitcoin and currently still in Ethereum. It's the generation 0 of consensus algorithms, which is proof of work. In essence, the way this works is, well, at least in Bitcoin, the way it works is that you have the blockchain. From a specific node, the miner would retrieve pending transactions, and they'll engage in the proof of work process, which on average takes about 10 minutes. The difficulty of the computational problem being solved in proof of work will adapt to make sure it takes about 10 minutes. And then the block and the proof of the block, which is the final hash, is returned to the node. And the blockchain is, well, then this is then broadcasted, and the blockchain is updated for all nodes. To give a bit more detail on this. So the actual computational problem being solved here is that you want to use the nonce, which is basically just a variable, a number, which we implement. We use that alongside the previous hash and the previous block, alongside the hash of all the transactions and other information within the block to create a new hash. The problem being solved in proof of work, in Bitcoin at least, is you want to have a certain number of zeros at the start of the hash. When you get the first miner to get that, then broadcasts this and gets reward, which ends up being both the mining reward and the transaction fees. One of the main reasons this solves the conflict resolution problem is that a lot of miners are working on the problem at the same time. And it's not a problem that can be solved very quickly. It takes a long time and requires a lot of computational power, meaning that the first miner or the first group of miners to solve the problem are the ones that determine the content of the newest block. Which means that the only way to take over the network is to have 51% of the computational power, which is basically called the 51% cap. It hasn't really happened so far on any major cryptocurrency. But this obviously has disadvantages. It uses a ridiculous amount of computational power and electricity, and it's pretty damn slow. So it's quite hard to make it scale well. So this is just an example of a mining farm. I think an Ethereum mining farm using application-specific chips. So there's the concept of proof of useful work. What if, instead for this computational power, what if we use the computational power to solve a useful problem rather than just creating hash functions, like solving hash problems? Does anybody have any ideas of what kind of problem to solve? Yeah?
You could use it in a way like folding atoms or atoms, or there's big projects where we want
Now, the issue with that is you want to be, one of the problems you want to solve here is that you want to be able to prove the integrity of the block, so you need in some way to be able to prove it would have to be somewhat in some way related to the contents of the block so you can prove its integrity. And also you would want the problems to not be in any way finite. And you'd also have to require it would add an additional level of trust, since you need to trust the software and hardware of the organizations you're doing useful work for. So there are some issues there, but it is possible, especially in a permissioned blockchain that would be used by this piece of scientists. But any other ideas? Go on.
generating Bitcoin.
Yeah. Again, the issue there is that that does fulfill most of the criteria, but again, the issue is that it wouldn't be relevant to the contents of the block itself. So an example, this is basically a summary of all the properties that you would have to have in a proof of work needs to fulfill. So it's definitely possible, probably, to do proof of useful work, and there have been several ideas that have been proposed that are being considered, but there's nothing serious that has been tried so far. So you want the solutions to be easy to verify, which with hash problems it is. You want it to take some time to find the solution, so people have to work for it. So you need solutions to be hard to find. You want to be able to precisely quantify how difficult the problem is, so you know how long it will take and so on. And you want it to be inseparable from the block is secure, so you want it to be able to prove the contents of the specific block. And ideally, you want the number of problems to be solved to be infinite. So if at one point, you don't at any point become unable to engage in the mining process. Otherwise, at one point, once you run out of problems to solve, the network just dies. Yeah, so far no useful work that meets the criteria has been found. It's quite sad. But that's where proof of stake comes in. Now, I think the first cryptocurrency that came up with this was Purecoin, and then it's been touted it's been supported quite a bit by Vishal Soomaney, the founder of Ethereum, ever since. So the basic idea here is that every account has a certain chance of generating the next block. So people aren't competing to solve a computational problem here. The chance is greater if you have a greater staking system, as they follow an assumption that if you have a stake in the system, such as if you own a certain amount of the tokens in the system, you're less likely to act maliciously, or less likely to try to compromise the system, and it's in your best interest to make sure the system runs smoothly. There's two major types. One would be randomized block selection. In this, the more tokens you own, the more likely it is for you to make the next block. So that's basically a very basic example, which is when you meet that condition, you would, if at any point a node meets that condition, whereby the diff would be the variable that just signifies the difficulty of finding a suitable node, and the balance would be the amount of tokens a certain node owns. Whenever a node meets these criteria, they'll give them the permission to create the next block, and they would then get the transaction fees involved in that in the creation of that block. Now, this does provide a considerable benefit in the fact that it's theoretically more secure than proof of work, since to take over the system here, you would need to take over about 51% of all the tokens in the system. So if you were to do this for, let's say, with Bitcoin, you would need to own 51% of the Bitcoin to be able to take over the network. since you would need to have the majority of the balance in the system. Meanwhile, for proof of work, you need to have 51% of the computational power of the miners. So it's theoretically more difficult here. And also, in this case, it's also much more efficient as people are competing by doing computational problems. And the second one is coin age-based selection, which is the idea that the people that hold tokens for more than 30 days without using it, their tokens then become eligible for, tokens are then taken into account when selecting the next block generator. So there's usually this peaks at 90 days. So between 30 and 90 days, your blocks, your tokens will be considered for that. Once your tokens have been used for that process, their age returns to 0. So you can't just hoard tokens for a long amount of time and make them have a ridiculous age and therefore temporarily take over the system. So stakeholders, you would need to have a majority of all coins in the network to be able to attack the network. But then there's a variant of this called Delegated Proof of Stake. This is where there's a limited number of delegates in the system, and each node gets to vote on a delegate. This would be similar to Parliament, where we vote on our representatives. So each node gets to vote on a delegate, and you can vote for yourself. Your voting power generally is proportional to the number of tokens you own. So if you own more of the cryptocurrency or token in the system, you get to vote on, you get more voting power for the delegate. And delegates act as nodes which are capable of adding transactions and blocks to the rest of the network. So the reason they're incentivized to do this is that they get compensated for doing this by the transaction fees. The more voting power that's been used to vote them in, the more power they have, basically, and the more authority they have in the system. And this also allows for voting in regards to determining any changes to the network. It's generally more efficient than traditional proof of stake, and people can get voted out anytime. There's a lot of disadvantages to this as well. But if anybody does start acting maliciously, you can get voted out. And often they also provide incentives to people voting for them by giving them a share of the transaction fees. So they can give a bit of corruption in there. But the good thing is that this allows the delegates to be able to have a lot of delegates to be people that have a lot of in-depth knowledge of the network itself, and they have a considerable stake in making sure it stays stable, since they're getting a steady stream of income from the transaction fees.
How does that work?
That actually I want to have a talk regarding that coming up, but it would depend from network to network. So here we're giving an example of Lisk, but there's a lot of cryptocurrencies that are implementing delegated proof of stake, and each one has implemented voting in a different way. I think in a lot of them it's just based they get the ability to do it in the wallet, so it's quite straightforward, where you just provide the public key of the node that you want to vote for. But it really depends on the cryptocurrency itself. And I can give you examples of it at the end of the talk if you want. But yeah, this way the delegates are people that have a considerable stake in the network, and they have considerable knowledge of how it works, so they can work on voting for future changes to the network. Let's say if there's a way to make it more efficient, they can vote on a future fork or something of the sort. And another one would be proof of elapsed time. So now this one's a bit interesting because it's specifically designed to work on permissioned networks rather than public ones. So this would be a private blockchain network that you would need to be invited to join. Example of this would be Hyperledger Sawtooth, which is being developed by IBM, and the consensus algorithm itself was developed by Intel, I think, in 2016, and it's been gaining popularity within permissioned networks ever since. The essential, the basis of it is each node in the network is given randomly given a amount of time they wait idly. The first node to wake up, or for their waiting time to end, gets to generate the next block. So the important thing here is to make sure that nobody can reduce the time their CPU sits idle, or can wake up faster than everybody else. And that's where Intel's SGX comes in, which is, I think, secure guarded something. I forget. Each participant is given a random timer, and the first time it expires wakes up. And this relies heavily on Intel's SGX protocol, which is the main reason Intel came up with it. Now the problem here is if there's a fault found in that, then we're going to have then the entire consensus algorithm falls apart. So you're relying on hardware security here as well. But the reason this is, Intel SGX stands for Software Guard Extension. So it basically allows you to create an enclave which can contain secure processes and code which is theoretically it's theoretically much harder for a malicious actor to get to it and make changes to it. It gives considerably greater ability to reduces the attack surface and makes it easier to defend the application. Yeah, there's plenty of reading behind it in regards to why it's so impressive, and thus far it does seem extremely secure. Sorry about that. And the proof of last time completely relies on this being secure. So this is used to create a trusted execution environment that produces a signed attestation from within the platform, which lets you know that the node is using the trusted code provided by the network, rather than using creating an edited version that lets them always win. Yeah, this is safe, and this is efficient, but only safe as long as SGX remains secure, and as long as nobody's trying to fault with that. And also is only works with permission blockchains in reality. So I think that's all I had time to write, and I'm expecting myself to get tired by now, so I decided to end it there. But we do have there's a lot of other really consensus algorithms that we want to talk about in future talks. This was just a relative introduction to consensus algorithms. And to learn more about this kind of stuff, you can join our Facebook group and check out our website, where we're going to be writing a few blogs regarding the topic. We already have one up about sidechains, which is a way to improve scalability of blockchain. But aside from that, we also have a really cool talk coming up on 11th March, which is basically about regulation around blockchain in industry mostly. So confirmed speakers at the moment include a director from Deloitte, as well as I forget the title of the other speaker, so we'll let you guys know over time on Facebook. But yeah, are there any questions so far? Okay. If anybody wants to come up at the end, to talk up front, that would be great as well. Or that's all we're doing today. So, and that's all. Thank you.